So now that we've talked about regression, which is finding the equation of a line, I want to talk about correlation. And correlation is, we're going to do linear correlation. And I want to mention that correlation isn't really what we want to do. Correlation tells you how strong a relationship is, but a more important measure of strength of relationship is actually what's called the coefficient of determination. And so we're going to look into that kind of concept, but I want to just mention a little bit about correlation and what it is. We are doing linear correlation in this course. I also want to mention that its correlation is between two variables. And that is a problem if you have more than two explanatory variables, correlation won't work very well. But before we do that, I'm going to go ahead, before I talk more about what we do instead, I'm going to talk a little bit about what correlation means and just what the concept of it is. I'm going to draw a bunch of graphs, and when we're going to talk about those graphs and what they look like. So this one, I have that one. So this is a bunch of dots coming downward, a bunch of dots going upward. They're kind of tight looking dots. I can also have dots that are coming up but not as tight. I can have dots that are kind of going up, but they're really all over the place, not real tight at all. I could have dots that are just all over the place and you can't even tell if they're going up or down. Or I could actually have a graph, and again, these are just the dots you're going to have. You can have dots that might look something that looks like a U. And I want to talk about what the correlation is in each of these. So this first one that had the dots going down and kind of tight looking, this is known as, they're fairly tight. That looks like there's a nice line. They look like they follow that line really well. We say that this is a strong correlation. Also, since it's going down, we call it strong negative because it's going downward. This one, on the other hand, is going up. It's still strong. The dots are still really close to each other. So it's strong, but it's going up. So we call that strong positive. The third one, where the dots are not nearly as close, they're still going up. So it's still positive, but they're not nearly as close as the strong. So you might call this one moderate and positive because it is still going up. And what up means is that as X is increasing, as your explanatory variable is increasing, your response variable is increasing. The one where the dots are kind of on a general trend upward, but are really kind of all over the place, this one's more what we call weak correlation. It's still positive because you can see a positive trend to it, but it's pretty dang weak. Where the dots are all over the place, this would be no correlation. And the one where it's a U-shaped, this U-shaped is also, it's not, remember, correlation is about linear and a U-shaped is not linear. So this one still is no correlation. What I want to mention is that the no correlation doesn't mean no relationship. There's definitely a relationship between these dots. There's definitely a U-shaped, we would call that parabolic. There's definitely a correlation going on here. I mean, sorry, a relationship going on here, but there's definitely no correlation going on. The last two I just want to draw, now that we have that idea, is one where the dots are exactly right on the line. You're never going to really see this, but I just want to point this one out. This is called perfect positive because the dots fall right on that line. The other one would be, again, the dots falling all along the line, but it's going down. This one would be perfect negative. Now, the other thing that's more important is what we call explained variation. Explained variation is also known as the coefficient of determination. And explaining how much variability in the y variable is explained by the x variable or variables. The reason we say it this way is everything has variability. There's variability in everything we do. If people are the same, if we're, let's say we're looking at height versus weight, And if person's height is higher, then their weight is higher. And so we have all this idea of what's going on here. But we want to be able to actually explain kind of how much variability is there. The fact that there's going to be changes in the Y variable. So I'm a certain height. Everybody who's my height is not my same weight. We all have a variability, all have changes in what our weights are. So the question is how much of that change in somebody's weight is explained by how tall they are. And the fact that we have different people with different weights in the same height, how much is that explained by the height, or are there other factors involved? And in fact, with weight, there are definitely other factors involved. So we want to look at those ideas. So we're looking at how much is explained by that X variable. And the reason I say variables is because coefficient determination actually will work for multiple explanatory variables. So that's what's nice about it. It is looking at the formula for it is explained variation, explained variability, how much is explained by the model, divided by the total variability or the total variation. The symbol for it that we use is R squared. I have a small r there. I've also seen capital R. You might see it either way. And in fact, if you're using multiple explanatory variables, you probably want to use the capital R squared. And so that's the symbol we use for that. I do want to talk a little bit about how we calculate the coefficient, the correlation coefficient. It's known as the Pearson correlation coefficient. It's for the sample value, it's an R, and you do some weird, crazy formula here. We're not going to do that formula. But what you're basically doing is the top of this formula takes that as X values and centers them around their means. And so it recenters your origin, you can think of it that way. And the denominator kind of scales it. So what happens is you get the values are always between -1 and 1. So that means I can go back to this picture we have here, and we can kind of put in some values here of what we think those values are. And what those values are is that strong negative, well, let's do the strong positive first. This would actually have a value of, let's say, R equal to, since closer you are to 1, actually, let's go do the perfect first. That will actually help us a little bit more. Perfect positive would be an R exactly equal to 1. So when we say R goes between -1 and 1, 1 means we're perfect correlation. Perfect negative would be R is equal to -1. You're on the other side. So a strong positive correlation would be an R of about, I don't know. And again, this is just kind of guesstimation, maybe like 92.92. Strong negative would be an R of about equal to, well, it's negative, so there's a negative sign on it, and 0.93, let's say. Moderate positive would be an R of around, let's say 0.73. And again, these are just approximates. I'm just making these numbers up. I have no idea what the R's really are. It just gives you an idea of what we consider moderate. Weak might be like an R of 0.32. No correlation means you have an R really close to 0. You may not be perfectly 0. There might be something slightly different from 0, but if you're close to 0, it would mean you have no correlation. This one also, no correlation means you're close to 0, but that does not mean you have no relationship. An R being close to 0 just means there's no linear, the strength of the linear relationship is really small. Does not mean anything more. Doesn't mean anything about the relationship. It's whether there's a relationship. We're actually going to do all these calculations using R. So I want to show you how we can do these. So we're going to go back into the R and get into RStudio here. And I already have the COVID data in there, so I'm not going to read it in again, but I could read it in again if I needed to. So here's my COVID data again. And what I'm now going to look at is trying to put in this. I want to calculate this. So the first thing I need to do is I actually need to calculate my linear model. But I'm going to call it linear model out. I'm going to give it a name, and you can call it anything you want. I happen to like linear model out because I'm taking, this is the output from the linear model. That's why I call it that. You can call it anything you want. You can call it cream for all I care. I don't care what you name it. It's just a name. Just like you name your cat or dog, It's just, or your pet, this is just a name. And that is going to be your LM, LM for linear model. And then you're going to put in your response variable, always comes in first. So that would be the per simp. And then your explanatory variable, mask. And then we have to tell it where the data is. So data equals COVID. And then we're going to hit enter. And again, it's going to look like nothing actually happened. But I notice over here, I now have a linear model out over here in my data, my environment. Now that I've done that, I actually can do summary of the lm.out. And I'm going to go ahead and copy this over so we can kind of play around and show you what all these things are. But it gives you this big amount of information. So I'm going to go ahead and put this in. And there's a couple of things I want to point out. First off, again, these are just what I typed into R, so just gives you an idea of what I typed into R. Then we have our linear model formula. This is just telling you what it used to do this formula based on what you told it. So make sure that this is matching what you want to tell it. Again, it's always your response variable and then your explanatory variable. It gives you a summary of your residuals. So it's just kind of summarizing what those residuals are. Just give you the basically the fine number summary of those. It also gives you the coefficients. And what's nice about this is that those are your regression line. So you can also get your regression line from here, not doing the other thing first. You can just do your regression line straight from here. Again, the coefficients, those are your slope and y-intercept. Notice this one says y-intercept. That's your y-intercept number right there. So this is the y-intercept. This is your B. And then the coefficient of the per mask was your x. So the coefficient of that is your slope. So that's your m. So I could write my equation from this. And I can write down that my y hat is equal to 114.83 minus 1.085 times x. Again, I'm using x and y for my variables. You don't have to. You can use the names of the word if you'd rather, the names of the variables if you'd rather not do that. I do want to talk a little bit about the slope. It's negative, which means it's going down. And remember what a slope means is that you're increasing your x by 1. So as I'm increasing my x, I'm increasing the number of people, the percent of people who wear masks in public most or all the time. I will then decrease, hence the negative sign, the percent of people you know who have symptoms by 1%, 1.1%, let's say. So what this represents, that slope represents for every increase in x, you will decrease your y by 1.1% in this case, because these are percentages that we're dealing with. So remember, this is the y is the percent of people who know somebody with a symptom. So if you increase if more people are wearing their masks in public, most of the time or all the time, then you will be decreasing the number of people you know with symptoms by 1.1% of people. So that's what that slope represents. We don't need the rest of this information just yet. The standard error actually matches with that number there. The T represents there and the P represents there. We don't need those just yet. We'll need those in a little bit. We don't need the significance level either. We don't need those code things. But we do need what's down here. And remember, I told you that we had r squared was what the coefficient determination is. And this actually says multiple r squared. So that number right there is your coefficient of determination. So that's your r squared. This adjusted r squared adjusts for a little bit about the variables. Don't worry too much about that. We usually use the multiple r squared one and not the adjusted. And so we have that information. That's what we need to have. And that tells us our coefficient of determination. Now, what I want to do is I want to interpret what this means. So the interpretation of this means that 75%, because that's about 75% of, and this can be done as a percent, because if you go back to this formula, coefficient of determination, it is the amount explained over the total, so that actually will be a percentage. By the way, the coefficient of correlation coefficient is not a percent, it's not over a total. So this is not ever written as a percent, but the coefficient of determination can be written that way. So this means that 75% of the variability in the percent of people in a state that know someone with symptoms is explained by how many people, or the percent of people who wear masks in public, who wear masks most or all the time. And that's a pretty high number. So I want to mention that that's a pretty high percentage. 75%, that's pretty dang good of actually explaining that variability. So we're actually able to say that if I know a state, a state that actually has a lot of people who wear masks, then I know that there will be less people who are, I know that are infected or have symptoms. If that percent, if the percent of people who wear masks is smaller, then I would actually have more people who I would know, the percent of people that I would know with symptoms would be higher. So I actually can use that to explain that. And that's very important to know. And that's why the CDC is recommending that you wear masks, because they know these statistics and what's happening. I do want to mention how you can get the correlation coefficient. I want to point out again about the fact that the coefficient of determination symbol is R squared. The symbol for the correlation coefficient is just R. So that means all you got to do is take the square root of your R squared value and then find out what your R is. So going back to this, my R squared value was 0.75. We'll get a few more decimal places here. 7541. I can take the square root of both sides and that will give me R. But remember, when you take the square root, you need a plus or minus sign. But we actually don't want a plus or minus sign here. We actually want to know what sign we want. So remember, when you take the square root of both sides, you need to put that plus or minus sign on unless you know which sign it is. So in this case, we do know what sign it is. I can get the sign two different places. One is that I know that I had a negative slope. I know it was going down, so I saw generally it was heading down. And also I noticed that the slope here from the output is negative. So if your slope is negative, then this will be a negative number. If your slope is positive, this will be a positive number. So I don't need the plus or minus. I already know it's going to be negative. I can actually go back to R and have it calculate that for me. So in R, I can actually just type in right here. Square root is SQRT. I would take the square root of 0.7541. And it's 0.868. So I'll come back over here. I'll put this in. I'll paste it in here. And so I now can tell you that this number here is negative 0.868. Because it's negative, I know I have a negative correlation. And I know this is pretty close to 1. 0.8 is pretty close to 1. So I'd say it's strong. So that's the interpretation of your correlation coefficient. Is it strong because its number is close to -1 in this case, and it's negative because we have a negative sign there. This is the interpretation of the coefficient determination. I do want to mention the reason we like the coefficient determination is it can be used for when we have more than one variable of our explanatory variable. So I'm going to show you how to do that. We're actually going to have another variable that we want to look at. And if I go back to my data quickly here and look at this, I have more variables here. I have the state, I have the location, and I have the restrictions. And what might be useful here is for me to look at, could it be that there's less people I know with symptoms because, not just because of wearing masks, but because the state has restrictions. So restrictions may be another variable I want to look at. So I'm actually going to do where I'm going to add both of these together and deal with both of these. And so I'm going to first do a graph of that and see what it looks like. Again, I would like to graph the dot plot. I'm going to do that GF point. By the way, I can actually say that I would like the color to be the state, no, the location. So if I wanted to, I could actually do that and see what happens with that. So I put the tilde in front of the location just to say this is my variable. And then there's the percent greater than percent symbol says use this in the next step. I'm going to use this in the next step, and I'm going to do a GF linear model. And again, it will just use everything that we had in there already, so I don't need to type more in. It'll use everything that I put in the previous one in this next step. And then I can hit enter, and I can now see what's going on. So first off, I do have the dots. The different colors represent different things. The dots, the red dot represents we're in the Midwest, Northeast, and so forth. So I have that information there. But I just realized I'd made a mistake here. That's what I didn't do. So I want to do something more with this. So that just shows you the different colors. And notice I do actually have it based on what location we're in. But I would like to change that now. Instead of being the color based on the location, I would like to have the color based on the restrictions. Because it doesn't make as much sense to make the color based on location. It makes more sense to colors based on restrictions. And then I'll again do the linear model. Oops. Oh, shoot. Made a mistake. I did had a built-in. So I want the color now to be based on the restrictions. And so now I can see what's happening with those restrictions. And I can see some values going on here and what that looks like. So I can see it does look like, now major only had one dot, so it didn't draw me a line for that because you can't draw a line with just one dot. None only had 2 dots, so it didn't draw me a line based on that because we don't want to do regression with just 2 dots normally. But minor and major, minor and moderate had lots of them. So that's why we have both lines there. And you can see that when we had minor restrictions, we still have a negative slope happening. So it still is working that the mask wearing helps lower the number of incidents you see. Whereas moderate has a slope, but not as steep. So that means you're not going to see as much change by people who are wearing masks, because they're wearing masks doesn't actually make it so that you have as much of a change, because there are also restrictions and they're not going out, they can't go places. So you'll see still a change from wearing the mask, but not as big of a change with the moderate, but you still see it happening. So again, I'm going to go ahead and put this over here so we can kind of just, actually, I don't need the graph. We're just going to go straight to how we do this. I want to actually do another linear model out. And I'm going to call this one linear model out new. And I'm going to save this. And this is going to be my linear model. Again, you start with your response variable, which was the per symptom. And then I'm going to tilde with that with the per mask, your explanatory variable, but there's a second explanatory variable. So I want to add to that restrictions. And then data equals COVID. So by just adding in, if you have more variables, so if I wanted to put location, I don't think location is a great variable here. It doesn't make sense to do it, but I could do it if I wanted to. But I can see kind of what's happening. And now I've got that. And again, I'm going to do a summary of that. And I'm going to go ahead and copy this over so we can talk about what's going on. Okay, so what I'm seeing here is that now there's actually, it again just gives you the idea of what your equation was. You can see now there's actually a per mask, restrictions minor, restrictions moderate, restrictions none. It gave you equation, I gave you your, this is your intercepts. Sorry, this is your, I'm sorry, they're all kind of off of here a little bit. So your intercept for per mask. Oh wait, yeah. You can kind of see what's going on here. I'm having a hard time reading this for some reason, but it gives you the intercept value right here. This is your y-intercept, and these are your slopes. So you can see what's happening with these, and what there's not really a slope anymore in this case. You would actually just add these on. And so you'd have your equation is your y-intercept plus negative that slope times x plus that value, that coefficient. Again, these are no longer think of it as slopes, they're more just coefficients at this point. Coefficient times minor would maybe be 0, moderate would be 1, not, well, actually none would maybe be 0, minor would be 1, and moderate would be 2. And then you could just kind of add those on or add them, or when one is on, the other ones are off kind of thing, if that with a better idea. And those are how you would write the equation. And we're not going to actually write the equation. What's more important here is this number here, your multiple r squared. So again, I can do the coefficient determination here. Notice a little bit higher. Now it's 0.77, almost 0.78. So we've increased r squared by adding on this extra variable. Did it add enough? I don't know. Probably maybe not enough, but it did add a little bit for you to get to some ideas. So this is kind of what we do with these is we add these values on, and we can see kind of what's going on when we have these extra explanatory variables.